Hello, everyone. So today we're going to be talking a little bit more about reaction mechanisms with specific focus on high energy intermediates. So there are multiple ways you can generate a high energy intermediate along the course of a reaction. So one of the good places to start, because again, most kinetics tend to behave best in the gas phase, is by looking at a common trend in gas phase reactions, which is unimolecular isomerization or decomposition reactions. So we looked at this a little bit with dinitrogen pentoxide, but this is the fact that many gas phase molecules can essentially break apart or just undergo a simple isomerization, whether it's a ring formation or a linearization. Now, one of the things that is important to realize is a lot of these reactions do require the generation of a high energy intermediate. And this often occurs through the collision of two molecules. Because it's important to remember that while temperature tells us how much energy an atom has, it's essentially a kind of net average. So some collisions will leave certain molecules with a lot more kinetic energy, specifically in things like vibrations, than they would otherwise typically have. And so these collisions can leave a species to be essentially a high energy version, which then can go through the relevant reaction conditions. So a good general description was generated by Lindemann and Hinchelwood, which essentially described a simple case where I have two reactant molecules that can essentially collide together, leaving one of the molecules still in a low energy state and one in an activated high energy state. And this is going to occur with a given fairly low reaction rate. However, as there's probably a whole lot of A present, these molecules can then collide back together, essentially letting my activated or excited state A molecule fall back down to the ground state. But every once in a while, this activated or high energy molecule can undergo a conversion to a new product species, whether this is a decomposition or just a simple rearrangement. And this is going to happen with its own rate constant. And we can also imagine this kind of pictorially, where I'm going to have a high energy uh, uh, molecule collide with my original reactant of interest, which can then again activate it to uh, increase the energy to an activated state, which can then either decompose by the same mechanism, or it can essentially break apart into products, or again, a simple rearrangement. And again, the focus here is this A prime is going to represent this high energy active intermediate. And as such, if I'm going to describe it with kinetic equations, I am going to have to treat it as such an intermediate. So doing this, we can essentially break our system down into three key steps: the forward collision reaction, the reverse of the collision reaction, and again, the product formation. However, we're going to really be focused in on the rate of product formation, which again is going to be given by the rate constant for the second step times the concentration of my excited state system. Now, trying to figure out the concentration of the excited state system is much messier. However, we are aided by our good old friend, the steady state approximation. So all we need to do is find in what ways it's going to be generated and in what ways it's going to be consumed. So it turns out the generation of this activated complex is going to occur uh, as a second order reaction in A with a rate constant of K1. However, there are two reactions that can consume this this activated high energy intermediate. The simplest one being this third term, which is again first order in my high energy intermediate with a rate constant of K2. But we also have a reaction step that's going to be first order in both A and my high energy intermediate, with again dependency on the rate constant of the reverse reaction. So using this and the fact that we're assuming that the concentration, at least after an initial induction period, is relatively constant, I can then rearrange the equation to isolate the concentration of my high energy intermediate. So in this case, we can then combine the two coefficients of the terms shared with the consumption reactions, which then lets me essentially divide both sides by this combined coefficient of the reverse rate constant times a plus, again, the rate constant for the second step. So this gives me a unified expression for the concentration of the steady state concentration of my high energy intermediate, with again a dependency upon the concentration of my reactant, because again, more reactant, we would typically expect more high energy intermediate, and again, the three rate constants. However, it's worth noting that what we're really interested in is the formation of my product species, which again, so this lets me go ahead and insert the concentration of my high energy intermediate into my kinetics equation for the rate of product formation. And then I'm left with a, let's be honest, not exactly the most pretty rate equation, but far from the worst one we've dealt with. So let's go ahead and look at kind of these limiting circumstances. So under limiting conditions, typically we're going to see the product formation is going to be a lot slower than essentially with the reactant molecule, again, interacting with itself. So if the high energy intermediate tends to relax down to the ground state much more than it undergoes reaction, this is going to be a much more common case. And in this case, we have the first term tends to dominate, so I can essentially drop out the rate constant for the second step of the reaction. And this leaves me a much prettier reaction rate expression, as first I'm able to get rid of any addition in the denominator, and then we quickly notice that we're able to drop drop an order in our dependence on our reactant concentration. And what we're left with is a first order dependence on my reactant with a little bit messier of a rate constant. So one good way to try and look at this is that under this circumstances with rapid high energy intermediate formation and degradation, we're going to see kind of what we originally expect, which is a first order reaction. It's still A going to product. But the real devil's in the details here. And that's in the nature of the rate constant, because our rate constant is going to be slightly modified based on the one we'd expect just from the second step dominating, as I still have a dependence on the ratio of my forward and reverse reaction steps. So one of the important things we can do is try and differentiate the Lindemann-Hinshelwood mechanism from a typical unimolecular reaction mechanism where I don't have to go into a high energy intermediate. And one of the ways to do this is to try and fit it to a linearized form of our full reaction, full rate equation. So what we're going to do is focus most specifically in on this wonderfully messy rate constant, which is going to show a dependence upon the concentration of A, which is going to, and we're going to thus see this rate constant change based on the concentration of our reactant present, which is not a behavior we would expect from a simple first order mechanism. So what we can then do is try and linearize this equation by taking the inverse of this rate constant, which then lets us flip the right-hand side of our mechanism, of our equation. Most specifically, the reason why this is beneficial is it lets me split apart this pesky addition term into two expressions, being K1 prime times the concentration of our reactant over K1, K2 concentration reactant. And again, a similar sort of expression for the second term. And then, as always, I'm going to look for terms that cancel. In this first part of the expression, I'm going to watch the concentration of A disappear because it'll essentially cancel out. In the second part, I watch the rate constant for the second step of the reaction disappear. So what I see here is that I should be able to plot 1 over the rate constant versus 1 over the concentration of reactant. And by plotting the inverse of these two terms, I should essentially see a linear line, which should help get me, first of all, from the slope, I should be able to get the rate constant for the activation of my high energy intermediate. And then from my intercept, I should be able to back out my remaining two rate constants, or at least the ratio of the two values. So this can be, again, a very useful sort of feature. But one of the things that is worth noting is this mechanism does start to often break down under high concentrations due to the uneven nature of these uneven nature and high frequency of collisions of A with itself. However, there are also many other types of high energy intermediates. So one that often brings a lot of attention is the thermal decomposition of ozone. So ozone can essentially decompose into diatomic oxygen, which we brought up several times before in the class. But the real thing that kind of makes this unique is going to be the mechanism, because it's not just that two ozone molecules suddenly collide together, because that's going to be, well, frankly, a little unusual, because ozone doesn't exactly have the highest concentration. Instead, what I'm going to tend to find is that ozone will decompose into O2 and a high energy oxygen atom intermediate, which again can be thought of as a diradical species. So this guy is not exactly favorable. However, we can also have the reverse reaction regenerating ozone, which wouldn't exactly be uncommon due to just how high energy this intermediate is. But it's also possible for this high energy intermediate to essentially collide with ozone from a slightly different angle, which would cause my ozone to break apart into two oxygen molecules. Again, good old fashioned oxygen gas. And again, it is worth noting that this is only one potential ozone decomposition mechanism, though many of the others rely on the presence of other species being present in the atmosphere. However, we can essentially try and use this mechanism to develop a rate for the decomposition of ozone, which again is a very special interest because we like to keep ozone in our ozone layer. So we can give the rate for the decomposition of ozone based on the production of ozone, which only occurs through the reverse reaction, which is going to be first order in oxygen and molecular oxygen and first order in atomic oxygen. While the decomposition can occur via two different mechanisms, both a unimolecular mechanism that's only first order in ozone, as well as with collision of with the oxygen atom, which is going to be first order in ozone and the oxygen atom, all with the relevant rate constants. However, what we run into here is the fact that I have this in terms of product, reactant, and intermediate. So we have to rearrange this equation to essentially we first need to describe the concentration of our high energy atomic oxygen intermediate before we can really determine the full rate expression for the decomposition of ozone. So let's go ahead and start with our good old friend steady state. So again, we'll start with, our consumption reaction. And now we can try and determine the concentration of our atomic oxygen using, again, the steady state expression, where I can generate atomic oxygen in my first step through the decomposition of ozone, which again is first order, but I can also consume it in two different bimolecular reactions. One being the reverse reaction where it combines with diatomic oxygen, and one where it combines with ozone itself, with again, each having their relevant rate constants. Then we use our classic strategy, try and isolate all terms that include the oxygen atom over to the right side, getting rid of our negative sign. So now we have essentially a wonderful combined rate constant, or a combined prefactor for molecular oxygen concentration, one of the terms is first order and molecular oxygen, and one is first order in ozone. However, I want to try and isolate my atomic oxygen concentration. So I'll divide both sides by this rather wonderful precursor value, and I'm left with a beautiful little expression for our atomic oxygen. However, the reason I did this is because what I was really cared about is the rate of reaction of ozone. So I need to go ahead and insert this expression back into my ozone rate. And again, hope that I'll start to see things cancel. So when we do this, well, not looking so good right off the start. We don't see a lot of terms essentially cancel here. But we do note one particular advantage here, most namely that both the first and the third terms share a common denominator. So we can do a very similar trick to what we did with dealing with dinitrogen pentoxide and essentially try and multiply uh, our prefactor for ozone by one, in this case, one being this wonderful little sum term divided by itself. So doing this, I can then multiply by K1, and this case, we again get very lucky because K1, K1 prime, O2, O3 is the same thing as my first term. Then I watch the signs, plus on the first term, minus on the second term. They'll essentially annihilate out. That leaves me with negative K1, K2, O3 squared. Yes, squared in ozone. So this generates, this is the same as the third term, but they now share signs. So this simplifies itself down to negative. Again, I apologize. This should be a 2 K1, K2 ozone squared. So this gives us an overall rate. This gives us a numerator that is second order in ozone. And after this, we're going to have to pay very close attention to conditions. Under high ozone conditions, we're going to essentially watch the second term in the denominator dominate, and we have a reaction that's first order in ozone. But under low ozone conditions and high oxygen conditions, which is frankly much more common, we'd expect this term to be second order in ozone and inverse of first order in oxygen. So this would essentially indicate that increasing oxygen concentrations would slow the rate of consumption of ozone, which is not something that we'd essentially predict just from brief inspection. So this is, again, one of those things that, one of those reasons why paying very close attention to the reaction mechanism can be very important, because it can provide us great information about the kinetics that we never get from looking at the overall reaction. So that brings us to the end of kinetics. Next time, we're in for some wonderful stat mech. Till then, take care.